When factoring polynomials, it's often helpful to recognize special products. We get the following formulas by multiplication, but they turn out to be useful when factoring. The first formula tells us how to factor a difference of squares. To factor a squared minus b squared, we do a minus b times a plus b. Next, we have perfect square trinomials. These are trinomials that are also perfect squares of binomials. A squared plus 2ab plus b squared can be written as a plus b quantity squared, and a squared minus 2ab plus b squared can be written as a minus b quantity squared. These two formulas help us recognize when a trinomial might be a perfect square. That is, when the first and third terms are perfect squares and the middle coefficient is even. The next two formulas indicate how to factor the sum or difference of cubes. I refer to these as the SOAP rules. The acronym SOAP helps me remember the signs in the factorization. S stands for same sign, O stands for opposite sign, and AP stands for always positive. To factor the sum of cubes, a cubed plus b cubed, we consider the two bases that are cubed. We get the first base a plus, which is the same sign, the second base b as one factor. The other factor is a prime trinomial of the form first base a squared minus opposite sign, the product of the two bases ab, plus, always positive, the second base squared. Again, the acronym SOAP stands for same, opposite, and always positive, which gives the signs in the factorization. To factor the difference of cubes, a cubed minus b cubed, we again consider that the two bases that are cubed. We get the first base, same sign, second base, and our second trinomial factor has the first base squared, the opposite sign, the product of the two bases, always positive, the last base squared. For our examples, let's factor first using the difference of squares formula. To factor x squared minus 16, we notice that we have the difference of squares. This is x squared minus 4 squared, and so the formula says we factor by using x minus 4 times x plus 4. We can multiply back at the end to confirm that our factorization is indeed correct. To factor 4x squared minus 25, we notice that we have 2x squared minus 5 squared. And so our factorization looks like 2x minus 5 times 2x plus 5. Finally, to factor 25x squared minus 36y squared, we notice that our first term is 5x squared, and our second term is 6y squared. So this difference factors into 5x minus 6 times 5x plus 6. Now let's consider examples factoring perfect square trinomials. We've got the formulas repeated here for convenience. We want to factor each polynomial, starting with x squared plus 8x plus 16. We notice that the first and third terms are perfect squares, and the middle coefficient is even. Thus, we have a potential candidate for a perfect square trinomial. We can try the factorization x plus 4 times x plus 4, which we notice by multiplication back is the correct factorization. Therefore, we have x plus 4 squared. Factoring the the trinomial 9x squared minus 12x plus 4, we notice again that we have a perfect square in the first term and a perfect square in the third term with an even coefficient in the middle. Since 9x squared is 3x squared and 4 is 2 squared, we can try the factorization 3x minus 2 times 3x minus 2. A quick mental multiplication confirms that this multiplication is correct, and we write our product more compactly as 3x minus 2 quantity squared. Finally, the trinomial 25x squared plus 20x plus 4 has a perfect square in the first and third terms and an even coefficient in the middle. We try the factorization 5x plus 2 times 5x plus 2. When we FOIL that back together, we get 25x squared plus a 10x outer product plus a 10x inner product plus 4. So we're going to write our correct factorization compactly as 5x plus 2 squared. Of course, we could have used the earlier techniques for factoring quadratic trinomials in these three examples. Recognizing special product forms just makes the factoring quicker and more efficient. Now let's consider examples that are sums or difference of cubes. Again, we have the formulas available for easy reference and want to factor each polynomial. To factor x cubed plus 8, we notice that the polynomial is the sum of cubes with bases x and 2. In one factor, we have the first base x plus the same sign, the second base 2. Then we get a trinomial factor of the form, the first base squared, opposite sign, the product of the two bases, always positive, the second base squared. To factor 8x cubed plus 27, we first notice that we have the sum of cubes with bases 2x and 3. So in one factor, we get the first base, same sign, the second base, and we get a trinomial factor of the form, the first base squared, 2x squared is 4x squared. Opposite sign, the product of the two bases, 2x times 3 is 6x. Always positive, the second base squared. 3 squared is 9. To factor x cubed minus 125, we notice that we have the difference of cubes with bases x and 5. Our first factor will look like x, same sign, 5, using our two bases. And our second trinomial factor has x squared, the opposite sign, 5 times x, always positive, 5 squared. Now let's mix things up and consider more complicated examples of factoring special forms. To factor x to the fourth minus 81, we must remember that even powers can always be written as perfect squares. So we have a difference of squares with bases x squared and 9. This will factor as an x squared minus 9 times an x squared plus 9, and we notice that x squared minus 9 is also a difference of squares that can be further factored into x minus 3, x plus 3. X squared plus 9 factor is a prime factor and doesn't factor any further. the sum of perfect squares will always be prime. Let's now consider 2x cubed minus 50x, which doesn't seem to immediately fit any of our special forms. We notice a common monomial factor of 2x that we can factor out, leaving a second factor of x squared minus 25. X squared minus 25 can be further factored as an x minus 5 times an x plus 5. If we want to factor the polynomial x squared minus 6x plus 9 minus y squared, it also does not immediately appear to be of a special form. However, if we look closely, we may notice that x squared minus 6x plus 9 is a perfect square trinomial. Replacing x squared minus 6x plus 9 with x minus 3 squared, and still having the minus y squared, we notice that now we have a difference of squares with bases x minus 3 and y. So we get a factorization that looks like x minus 3 minus y times x minus 3 plus y. To factor 48x cubed minus 24x squared plus 3x, we again notice a common monomial factor among all three terms. We can factor out 3x squared, and our remaining factor is 16x squared minus 8x plus 1. This trinomial is a perfect square which factors into 4x minus 1 times 4x minus 1. So our original polynomial can be factored 3x times the quantity 4x minus 1 squared. If we want to factor 28x cubed minus 8y to the 6th, we might notice that y to the 6th is y squared cubed, and 8 is 2 cubed, so we can write this as the difference of cubes with bases 3x and 2y squared. Now using the SOAP rule to factor, we get our first base, same sign, the second base as one factor. And then for our trinomial factor, we get the first base squared, so 3x all squared is a 9x squared. Opposite sign, the product of 3x and 2y squared. Always positive. We take our 2y squared and square it for a 4y squared. For our final example, let's factor x plus 5 cubed minus 27. Again, we have another difference of cubes with first base x plus 5 and second base 3. To factor our first factor, we get the first base, same sign, the second base, and then we get a trinomial factor with the first base squared, opposite sign, the product of the two bases, always positive, the last base squared. Now simplification of both factors produces x plus 2 times x squared plus 13x plus 49. You should check the details on that simplification step on the last example.